In this lesson, we're going to learn how to find any oblique asymptotes of rational functions. Now, another word for oblique asymptotes is slant asymptotes, and you're going to see why in a little while. But before we discuss how to find oblique asymptotes, if they exist, let's remind ourselves about previous lessons that are needed before we continue with this lesson. So, in one of the previous lessons, we learned how to find vertical asymptotes of rational functions. And we also learned how to find horizontal asymptotes. Okay? So make sure you understand those two lessons, finding horizontal asymptotes and finding vertical asymptotes, before you continue the lesson on finding oblique asymptotes. Just as before, remember, not every not every rational function will have a horizontal asymptote, nor will it have a vertical asymptote. All right, so just keep that in mind. All right, now let's talk about how to find the oblique asymptote of a rational function. Well, first of all, you may ask, well, what is an oblique asymptote? Okay, so oblique asymptotes, which are also known as slanted asymptotes, okay, they have this form, y equals mx plus b. Now remember, you may recognize this as the slope-intercept form of a line. So let me go ahead and rewrite this a little bit better. So y equals mx plus b. So remember, this is a line, right? So an oblique asymptote or a slant asymptote, same thing, is a line. So you may say, well, what does that look like in terms of the graph? Well, here's a graph of a rational function, and you see you have this slanted line, right? So this is the oblique asymptote. See the one that's at an angle? All right, so it's not horizontal. All right, so if you have an oblique asymptote, then you cannot have a horizontal asymptote. All right, so this is what an oblique asymptote looks like. Again, notice you have your vertical, all right, and you learned how to do that in a previous lesson. And basically all you do is look at your restrictions. Where's the domain restricted? So you cannot divide by 0, remember? So when x is -1, that's where you have your vertical asymptote. All right, but that's what an oblique asymptote looks like. That slanted asymptote, and it's a line. It is a line. All right, so it's very important to understand that an oblique asymptote or a slant asymptote, same word, same thing, you can use either word, is a line. All right, now, another important characteristic about oblique asymptote is this. So you may say, well, how do you know if you have an oblique asymptote? All right, here's how you can tell. A rational function may contain an oblique asymptote. It may not, all right, but it may. It does if the degree of the numerator is exactly 1 degree higher than the degree of the denominator. All right, so the degree of the numerator is exactly 1 degree higher than the degree of the denominator. So if you go back to this example where we had a oblique asymptote right here, what is the degree of the numerator? Well, the degree of the numerator is 2. What is the degree of the denominator? Well, the degree of the denominator is 1. Well, isn't 2 1 more than the denominator? Isn't the degree of the numerator 1 more than the degree of the denominator? So 2 subtract 1 is 1, right? Okay, so this rational function will have an oblique asymptote. Now, keep in mind that you just like you did when you found the vertical asymptotes, you need to make sure you factor, so that way, if any factors are reducible, you reduce. Now, if I factor out an x, here, I just want you to notice that no factor is reduced. Okay. All right. So, and also keep in mind that you will be asked to state what the oblique asymptote is, just like you are asked to state the vertical asymptote. And remember, when you name a vertical asymptote, a vertical line, it's always x equal. So your vertical asymptote here was x equal -1. So I'm going to just denote this as VA. And your slanted asymptote, I'm going to call it SA, slant asymptote. In this case, you don't know what that is, but it's y equal x minus 2. And you're going to find out how to determine that. So if you look at another example, another graph, see this graph right here? Do you recognize this is the slant asymptote, right? The slant asymptote. And so notice the degree. The degree of the numerator is 2. The degree of the denominator is 1. 2 is 1 more than 1. So you're going to have an oblique asymptote. And the equation of this slant asymptote is y equal x plus 1 in this case. And here's the vertical asymptote. See the vertical asymptote? And you see it's at x equal 1. So your vertical asymptote is x equal 1. You get that from the denominator, right? Get that from the denominator. And again, keep in mind, if it's factorable, you need a factor before finding the vertical asymptote, because if it's reducible, you reduce. So in this case, you could factor this as x minus 2 times x plus 1 divided by x minus 1, and nothing factors. So this restriction is going to be your vertical asymptote. Keep in mind about the characteristics of these that was discussed in previous lessons. Do you see how the graph goes towards the oblique asymptote on this side? So it gets closer and closer without touching it, and it gets closer to the vertical without touching it. Notice there's no horizontal asymptote, right? If you have an oblique, you will not have a horizontal. And see on this side how the graph goes towards the vertical and towards the oblique asymptote. So in a future lesson, you're going to learn how to graph these, and these are just rough sketches of the graph. But remember, it doesn't have a horizontal. Remember how to determine if a function has a horizontal asymptote? The degree of the numerator has to be less than the degree of the denominator, or equal. Okay? So you see here the degree is more, so it's not going to have a horizontal. It will not have a horizontal asymptote. And the same thing here. See how the graph oscillates towards the oblique and towards the vertical? See how that looks? All right. And then it crosses the x-axis 2 places. You're gonna learn how to determine that in a future lesson. And over here it does this. It goes towards the vertical, towards the oblique, without crossing either one. Okay? All right. So that was the idea of what an oblique asymptote looks like. So you have this slanted line that looks like a line. And make sure when you graph it in a future lesson that it's dotted like we have here. Okay, so now that we know what an oblique asymptote is, what it looks like, how to determine if a function has an oblique asymptote, let's look at some examples. All right, so let's look at examples of finding those oblique or slant asymptotes. How do we find them? So example number one. Let's suppose we have this function. F of x equals x squared minus 6x plus 7 divided by x plus 5. All right. Now notice you don't have a horizontal, right? Because the degree of the numerator is larger than the degree of the denominator. So you're not going to have a horizontal. You're going to have an oblique in this case because the degree of the numerator is 2, the degree of the denominator is 1, and 2 is 1 more than 1. So if it's 1 more than 1, right here, so if it's exactly 1 degree higher than the degree of the denominator, then you're going to have an oblique asymptote. Now this is not factorable, so let's go ahead and find the oblique. Now, you may say, well, how do you find the oblique asymptote? You're going to use long division. All right, and so let's look at that. So let's go ahead and do this. Let's divide this out using long division. So we have x plus 5 divided into x squared minus 6x plus 7. So remember to find the oblique asymptote, oblique asymptote, use long division, or you can use synthetic division if it applies. Synthetic division if it applies, okay? If applies. All right, now let's go ahead and so it'll be the first thing you have to do is use long division or synthetic division. Now I could have used synthetic division here, right? Because the divisor is linear and the coefficient of x is 1. Since the divisor is linear and the coefficient of x is 1, you could use synthetic division. But before we do that, before we do this using synthetic division, let's do long division. Most students, when finding the slant or oblique asymptote, they tend to understand it better if they use long division. So x into x squared is x, right? X times x is x squared. X times 5 is 5x. And then you subtract. So x squared minus 5x is 0. Negative 6x minus 5x is a negative 11x. And then you bring down the 7. Then you divide all over again. X into negative 11x is negative 11. Negative 11 times x is negative 11x. Negative 11 times 5 is negative 55. And then you subtract. And when you subtract, you get negative 11x minus itself, and that's going to be 0. Remember, all these, every time you do this, this has to cancel out like that. And then 7 subtract a negative 55 is a positive 62. All right. Now, you see this quotient right here? This quotient is the oblique asymptote. But you have to write it in this way. So remember, the answer. So remember, when we had the discussion, the oblique asymptote is a line, right? So when naming a line, you're going to say y equals. So y equals. So you're going to say y equals x minus 11. So answer, y equals x minus 11. And so that is your oblique asymptote. So that's the slant asymptote. All right, so very simple, right? Okay, let's do the same. Let's do this, but using synthetic division. Synthetic division. And I forgot to mention, but remember when doing long division, if there are any missing terms, remember you got to put a 0 in there, right? You got to put that missing term in there. Okay. So now be careful when using synthetic division. I've noticed that sometimes students will see this as a 5 and they'll say 5 right here, when in actuality it should be negative 5, right? So negative 5. All right, so be careful. And then you put your coefficients. So you're going to say 1, negative 6, 7. There are no missing terms, so you don't see any zeros here. Okay, bring on the 1. Negative 5 times 1, you multiply. That's negative 5. Add, you get negative 11. Remember that negative 11 right here? And then negative 55 times negative 11 is 55. And you add, you get 62. So remember that 62? All right, so there's your remainder, right? Okay, now this is where some students have trouble. They have trouble transposing this into an expression, into a variable expression. You got to remember, your dividend, the largest exponent was 2. So when you divide by x, this right here is now going to be 1x. Not 1x squared, but 1x. You always go 1 less. All right, and then this will be your constant. So that's where you see that 1x minus 11, that x minus 11. So be careful here. Many students have trouble with this. All right, so you got to be careful. Okay, so all right, so the answer, if you use synthetic division, will be y equals. Don't forget y equals. If you leave that y off, and if all you put is x minus 11, if all you have is x minus 11 as the answer, that's incorrect. You got to say y equals x minus 11. All right, so it doesn't matter. Doesn't matter if you use long division or if you use synthetic division in this case. All right, so that's number 1. Okay, let's look at number 2. Number 2, let's suppose we had this in number 2. All right, we have g of x is equal to 3x squared plus x minus 2 divided by 2x plus 6. All right. Now notice that you have an oblique asymptote here. All right, because the degree of the numerator is 2, the degree of the denominator is 1. So it's 1, the degree of the numerator is 1 more than the degree of the denominator. So you have the oblique asymptote. Now we have to find it. To find this oblique asymptote, we're going to use long division. We cannot use synthetic division. So remember, even though this is linear, the divisor is linear, the coefficient is not 1. So I cannot use synthetic division. So my only choice is to find the slant asymptote by using long division. All right, so here we go. 2x plus 6 divided into, this is already in descending order. There are no missing terms, so I get 3x squared plus x minus 2. 2x into 3x squared is, remember, be careful here because you end up with a fraction in this case. So 3x squared divided by 2x, right, is 3/2 x. So that's going to go here, 3/2 x. All right, then, all right, so then you're going to multiply. So you say 3/2 x times 2x. So 3/2 x times 2x. So the 2's divide out, and you get 3x times x is 3x squared. So 3x squared. And remember, if you're doing this correctly, these two have to be the same. 3/2 x times 6. 3/2 x times 6. 2 and a 2 is 1. 2 and a 6 is 3. 3x times 3 is 9x. So that's plus 9x. And then you subtract. And when I subtract, 3x squared minus itself is 0. X minus 9x is a negative 8x. Then you divide. Negative 8x divided by 2x is negative 4. And that goes here. Minus 4, and then you multiply. Negative 4 times 2x is a negative 8x. They have to be the same, remember? Negative 4 times 6 is a negative 24. And I forgot to bring down the negative 2. So don't forget to bring down the negative 2. All right, then you can subtract. Negative 8x minus itself is 0. A negative 2 subtract a negative 24 is the same thing as saying negative 2 plus 24, so that's 22. So there's your remainder. So you stop. Remember, you stop dividing because the degree here is 0. The degree of a constant is 0, and 0 is less than the degree of your divisor, which is 1. All right, so this right here, this quotient is your slant asymptote, but you have to write it as an equation. All right, so there's your slant asymptote. So the answer will be y equals 3/2 x minus 4. Okay? All right, so in this lesson, all we're interested in doing is you actually finding, well, what is that slant asymptote? Then in a couple lessons later, you're going to be graphing these. So you're going to end up having to do this yourself. All right, where you have to graph this line, graph the vertical line, and then determine in a rough way what the graph would look like. Okay. All right. So that was number 2. Okay, let's look at number 3. Okay, number 3, we have this. We have h of x is equal to x cubed minus 5x divided by x squared plus 1. All right, so x cubed minus 5x divided by x squared plus 1. Okay, so notice you're going to have an oblique asymptote here. The degree of the numerator is 3. The degree of the denominator is 2. Okay? And 3 is 1 more than 2. So you have an oblique asymptote. So notice I cannot use synthetic division because this is not linear. Even though you see the coefficient of x squared is 1, this is not linear. So you have to use long division. Now remember, there are some missing terms here. So you are going to need the missing terms. You will need to write them as zeros. So we have x squared plus 0x plus 1 divided into x cubed minus plus 0x squared, right? Minus 5x, and then I'm missing the constant, so you need that 0 as well. Okay, so let's do long division. X squared into x cubed is x. Notice I'm aligning my like terms. X times x squared is x cubed. X times 0x is 0x squared. X times 1 is just x, so plus x. Then you subtract, right? X cubed minus x cubed is 0. 0x squared minus 0x squared is still 0. A negative 5x minus x is a negative 6x. And then bring down the 0. Now, notice I cannot divide any further because the degree here is 1. The degree of this remainder is 1. The degree of my divisor is 2. Since the degree, once the degree is less, once the degree of the remainder is less than the degree of the divisor, you stop. So this is your quotient. All right, so the answer, my slant asymptote or oblique asymptote is y equal x. And that's it. All right, very simple. It is not a difficult process. It's very simple to do. All right. Okay, number 4. So let's do number 4. Okay, number 4, let's say we have this, number 4. All right, we have k of x is equal to x squared minus x divided by x plus 1. All right, and notice even if I factor out an x, I get x times x minus 1 divided by x plus 1. Nothing divides out. All right. So notice the degree of the numerator is 2. The degree of the denominator is 1. So I am going to have an oblique asymptote because 2 is 1 more than 1. So let's go ahead and use long division, and then now here we can also use synthetic division because this is linear and the coefficient of x is 1. So I'll do it both ways just to show you. But let's go ahead and use long division first. So I get x plus 1 divided into x squared minus x plus 0. So you're missing the constant term, so you got to put plus 0. Okay, x and x squared is x. X times x is x squared. X times 1 is x. And then you subtract. When I subtract, x squared minus x squared is 0. A negative x minus x is a negative 2x. And then plus 0. I can divide again because the degree here is 1. The degree here is 1. All right. So you stop whenever the degree of the remainder is less. So it's not less yet. So negative 2x divided by x, this is what you're saying. Negative 2x divided by x is negative 2. So that goes here. A negative 2 times x is a negative 2x. Remember, they're supposed to be the same. Negative 2 times 1 is a negative 2. And then you subtract. Negative 2x minus a negative 2x is 0. 0 subtract a negative 2 means 0 plus 2, which is 2. So that's your remainder, right? And this is your quotient. So the answer, that's your quotient. And remember, the quotient is going to be your line. So your slant asymptote. So the oblique asymptote is y equals, you must say y equals x minus 2. All right. Now, if you had used synthetic division, so remember to use synthetic division, you got to set this equal to 0. So x plus 1 equals 0, so you get x to be negative 1. So you got to say negative 1 if you use synthetic division, right? And so your coefficients, so you're going to say 1, negative 1, and 0. 1, negative 1, and 0. Bring down the 1. 1 times negative 1 is negative 1. Add, you get negative 2. Multiply, negative 1 times negative 2 is 2. Add, you get 2. Remember, that's your remainder, right, which is what we had here. Now be careful. So when using synthetic division, you're always going to go one less than the exponent in your numerator, the degree of the numerator. So 2 subtract 1 is 1, so you're going to say 1x. And then there's your constant. So your quotient, if you want to rewrite it again, is x minus 2, and that's what you saw here. So you don't forget though, don't say that the answer of the slant asymptote, don't say it's just x minus 2. If all you put is x minus 2, you're not going to get full points because you didn't tell me this in terms of an equation. What is the equation of that slant asymptote? The equation is y equals x minus 2. Okay? All right, that was number 4. Okay, let's look at number 5. So it's a very simple process, not difficult at all. Not difficult at all. Okay, number 5, we have k of x is equal to x squared plus 3x plus 2 divided by x minus 1. All right, now, this is factorable, so if you factor this, you'll get x plus 2 times x plus 1 divided by x minus 1. But there's nothing in here, no factors can be reduced. So let's go ahead and use synthetic division or long division here. I can use synthetic because the divisor is linear and the coefficient is 1. And I know I'm going to have an oblique asymptote because the degree of the numerator is 2, the degree of the denominator is 1, and 2 is 1 more than 1. So I'm going to go ahead and use long division. So get x minus 1 divided into x squared plus 3x plus 2. So x into x squared is x. X times x is x squared. X times negative 1 is a negative x, right? Then you subtract. X squared minus x squared, 0. 3x subtract a negative x is the same thing as saying 3x plus x, which is 4x. And then bring down the 2. Divide again. X into 4x is 4. 4 times x is 4x. 4 times negative 1 is a negative 4, and we subtract. 4x minus 4x is 0. 2 subtract negative 4 means the same thing as 2 plus 4. So that's 6. And so there's your quotient. So the answer, you're going to say the slant asymptote is y equal x plus 4. Okay? All right, so that was number 5. Now let's look at number 6. All right, now number 6, don't let number 6 throw you off. Here's number 6. You have f of x is equal to x squared plus 1 divided by x. All right, so you have f of x equal x squared plus 1 divided by x. Now, notice that in this case, the denominator is a monomial. So remember, when you're dividing a polynomial by a monomial, you're going to write it as 2 fractions. So you're going to say that's going to equal x squared divided by x plus 1 divided by x, right? And then reduce. So that's x squared divided by x is x plus 1 divided by x. And so this is your quotient. That is your quotient. Now, if you want to do long division, you can. You can do long division here. Let me show you. X into x squared plus 0x plus 1, right? You're missing that 0. You're missing that x term. So watch. X into x squared is x. X times x is x squared, right? Okay? And then you subtract. X squared minus x squared, 0. Bring on the next term, correct? X into 0x is 0, correct? And then 0 times x is 0x. And then you subtract, you get 0, and then you bring down the 1. And then this 1 right here is your remainder. Because remember, 1, the degree of constant 0, and 0 is less than the degree here, which is 1. So your quotient is just x, because x plus 0 is x. And so when you write it, you'll say x plus 1 divided by x. So the remainder divided by the divisor. And that's what you see here. So this is your quotient right there. That's your quotient. All right? And so the answer, your slant asymptote or oblique asymptote, is y equal x, right? And that's it. All right, so that was some examples on how to find the oblique asymptote. So every problem here, numbers 1 through 6, had an oblique asymptote. It had an oblique asymptote. All right. Now, uh, not all rational functions have oblique asymptote. Just like you saw, not all have horizontal asymptote. Not all have vertical asymptotes. All right. So keep that in mind. All right. Now let's look at this. Okay, so let's look at this set of examples. So the question is going to be, does the following rational function have an oblique or slant asymptote? All right, so let's look at number one. So number one, let's suppose we have f of x equals x cubed plus x squared minus 2 divided by x plus 1. All right, so remember, the degree of the numerator is larger than the degree of the denominator, correct? But you for you to have an oblique asymptote or a slant asymptote, remember an oblique or slant is a line. In order for you to have a line, the degree of the numerator has to be one more than the degree of the denominator. So look at the degree of the numerator. The degree of the numerator is 3. The degree of the denominator is 1. Well, that's 2 more, right? 3 is 2 more than 1. So you're not going to have an oblique asymptote. What you're going to have instead, if you do long division, you're going to have a nonlinear asymptote. Nonlinear asymptote, which means that the asymptote is not going to be a line. In order for it to be a line, the degree of the numerator has to be one more, exactly one more than the degree of the denominator. All right, so you're not going to have an oblique asymptote, you're going to have a nonlinear asymptote. Okay? All right, number two. Number two, let's suppose we have h of x is equal to x plus 1 divided by x squared minus 9. So are you going to have an oblique asymptote? The answer is no, because look at the degree of the numerator. The degree of the numerator is 1. The degree of the denominator is 2. The degree of the numerator is less than the degree of the denominator. So what are you going to have there instead? You're going to have a horizontal asymptote. So the answer is no. You will have h of x will have a horizontal asymptote. And I'm hoping you remember what that horizontal asymptote is. If the degree of the numerator is less than the degree of the denominator, remember the horizontal asymptote is the x-axis, or y equals 0. They mean the same thing. Okay? Number three. Number three, let's suppose we have k of x is equal to 2x plus 1 divided by 3x minus 2. All right, so look at the degree. So remember the question is, are you going to have an oblique asymptote? Well, you got to look at the degrees. The degree of the numerator is 1. The degree of the denominator is 1. They're the same. So if they're the same, what kind of asymptote are you going to have? You're going to have a horizontal. So no, k of x will have a horizontal asymptote, right? And then it'll be y equal. Remember, name a horizontal line as y equals. You name a vertical line as x equal. And remember how to do that is a coefficient of the leading term of the numerator divided by the coefficient of the leading term of the denominator. So 2/3. All right. Number 4. F of x is equal to x squared minus x minus 2 divided by x plus 1. Okay. Now, this is where you have to start being careful. So right off, you'll say, all right, you are going to have an oblique asymptote because the degree of the numerator is 2, the degree of the denominator is 1, and 2 is 1 more than 1. But You got to be careful. If you factor, if you factor that numerator, you're going to get x minus 2 times x plus 1 divided by x plus 1, and the x plus 1's divide out. So this rational function becomes x minus 2. And so notice that the denominator is 1 and the numerator is x minus 2. So notice that this is a line right away, right? That's a line. And notice you have some restrictions. So your restriction is -1, and you remember when the factors divide out, remember what happens there? That ends up being a hole, right? You get a hole there. You get a hole at x equal -1, at that restriction at x equal -1. And so here's what the graph looks like. This is what it looks like. So that's the graph that we just graphed. So notice it's a line, and you see that hole is at x equal -1. See x equal -1 here? You have a hole, and you're going to find out when we start graphing how to find that y coordinate. So the y coordinate here is -3. So you get a hole there. So this is what the graph looks like. So notice there's no slant asymptote. So the answer is no. No slant asymptote. No slant asymptote. And the reason there's no slant asymptote is because when you factored those factors divided out, that factor in the denominator divided out with a factor in the numerator, and you're just left with a line. All right, now I want to say this also. So no slant asymptote. In fact, if you, and this will be important when we start graphing these, notice there's no horizontal asymptote, there's no vertical asymptote, and there is no slant asymptote. So the graph has no horizontal, vertical. You may say, well, you have a restriction. The restriction is x equal to -1. Yeah, but remember when you talk about vertical asymptote, if anything divides out, that restriction is no longer vertical asymptote. It becomes a hole. It becomes a hole, and so that's what you saw here. So you're not going to have a vertical asymptote here. You're going to have a hole. So when we start graphing these, you're going to see this again. So you'll tend to remember it a little bit better. So there are no horizontal, no vertical, and no slant asymptotes. Now I want to say this. So suppose that you forgot. Suppose that you forgot to factor. All right, and you did this long division. So I just want to say something. You can catch yourself very easily by doing the long division. So if I do the long division, let's see what happens. X plus 1 divided into x squared minus x minus 2. So there are no missing terms. All right. So x into x squared is x. X times x is x squared. X times 1 is x. I subtract. X squared minus x squared, 0. A negative x minus x is a negative 2x. Bring on the negative 2. Divide. Negative 2x divided by x is negative 2. Negative 2 times x is a negative 2x. They're the same. Negative 2 times 1 is a negative 2. Subtract. Now notice what happens. Negative 2x minus itself is 0. Negative 2 minus itself is 0. Your remainder is 0. Whenever the remainder is 0, that means that this numerator here is factorable. That this is factorable, and then you'll be able to reduce. All right. So that's what that means. The remainder is 0. So that means that since the remainder is 0, that means that this quotient. Remember, that's your quotient, right? So that means that f of x, let me write this out, f of x, I'm going to rewrite this over, which was x squared minus x minus 2 divided by x plus 1 is just equal to x minus 2. And that's what you saw here. All right, so x minus 2. All right, so whenever the remainder is 0, whenever the remainder is 0, that needs to ring a bell. Something else is happening here. So the remainder is 0. Notice we did not, in this case, we did not get a slant asymptote. Even though the degree of the numerator was 1 more than the degree of the denominator, I did not get a slant asymptote. Notice in all the other problems we did, I just want to show you, just to show you something real quick. In all the other problems we did, I want you to look at the remainder. The remainder, all the problems we did. The remainder here, see for this one, the remainder was 1. Was it 0? No, it was 1. The remainder here was 6. Was it 0? Nope, it was 6. So that was your slant asymptote. The remainder here was 2. I'm going to use this one. The remainder here was 2. So there's your slant asymptote. Y equal x minus 2. So the remainder was not 0, right? Is the remainder 0 here? Nope, the remainder is negative 6x. So there's your slant asymptote, y equals 0. So in all the problems we did, the remainder was not 0. But this time, when I do that long division, I get a remainder 0. So this is not going to be a slant asymptote. So you're not going to have a slant asymptote. All right, so this reduces to this. There is no remainder. The remainder is 0. And so this right here is just a line. So this is a line. Your graph is a line with a hole. It's a line with a hole because when you factored the x plus 1's divided out, and it's a hole at x equal negative 1. Right? At x equal negative 1. So let's do one more just so you kind of make sure you understand this a little bit better. So let's look at this one. So this will be number 5. Okay, number 5. So look at number 5. We have f of x is equal to x cubed plus 3x squared plus x plus 3 divided by x squared plus 1. Okay? And so you're going to see this. So what students do is they see this and they say, all right, the degree of the numerator is 3. The degree of the denominator is 2, right? So the degree of the numerator is 3. The degree of the denominator is 2. So 3 is 1 more than 2. So they think that, all right, so I'm going to have an oblique asymptote. Okay, so let's go ahead and find it, right? Let's go ahead and find it. So you can do long division. So x squared plus 0x plus 1 divided into x cubed plus 3x squared plus x plus 3. Okay? And so now let's go ahead and do that long division. And so when I do that long division, I'm going to get x squared into x cubed is x. X times x squared is x cubed. X times 0x is 0x squared. X times 1 is x. And then I subtract. Notice what happens when I subtract. X cubed minus x cubed is 0. 3x squared minus 3x squared plus minus 0x squared, excuse me, is 3x squared, right? And then x minus x is 0. And then bring on the 3. So we're going to do that long division again. X squared into 3x squared is 3. 3 times x squared is 3x squared. 3 times 0x is, remember that was 0x here, is 0x. And then 3 times 1 is 3. And when I subtract, I want you to notice 3x minus 3x is 3x squared minus 3x squared is 0. This is 0, and this cancels out as well. So your remainder is 0, right? So look, you have another one where the remainder is 0. The remainder is 0, right? So that means this right here, so f of x equals x cubed plus 3x squared plus x plus 3 divided by x squared plus 1 reduces to just x plus 3. That's what that means. So that means that something is factorable here. That means, see how the denominator is 1? That means that if I factor this numerator, the x squared plus 1's divide out. And so you have a line here. You have a line. So there is no slant asymptote because the remainder was 0. there is no slant asymptote. The remainder is 0. So no slant asymptote. The remainder is 0. So let me show you how to remember. You have 4 terms, so let's factor by groupings. I can group these and factor this. So let me just remind you, you get x cubed plus 3x squared plus x plus 3. So in the first group, I can factor out an x squared, and you get x plus 3. X squared times x is x cubed. X squared times 3 is 3x squared. From the second group, the GCF is 1. So it's plus 1 times x plus 3. See how these are the same? So you can factor out an x plus 3, and you end up with x plus 3 times x squared plus 1. So that's your numerator. So this becomes x plus 3 times x squared plus 1 divided by the denominator, which is x squared plus 1. These divide out, and notice you get x plus 3, which is what we got when doing long division. Okay? Now, in the previous problem, remember, in the previous problem, we saw that, I can't find it, but we saw that there was a hole here, right? But there's no hole here because the denominator, there's no restrictions. No real number, if I substitute any real number for x squared plus 1 is never going to be 0. So see that's a sum of 2 squares? So there's no restrictions. So it's just x plus 3. All right, and there are no holes there. No holes. Because there's no restrictions for the domain. All right, but the point here is for you to know this. When you do long division and the remainder is 0, that means that you're able to reduce the denominator into the numerator. And so what you have here, you're going to end up with a line as a graph. So there is no, here's the graph. So there is no horizontal asymptote, there's no vertical asymptote, and there is no oblique asymptote. You just get a line, because remember, this is just equal to x. In this case, it's x plus 3. Y equal x plus 3. And notice there's no holes, right? There's no holes. In the previous problem, there was a hole because there was a restriction here, -1. Here, the denominator is never going to be 0. That's the sum of 2 squares. No matter what number I square, real number I square, add 1, this is never 0. And so you see a line with no holes. All right? And so that is, let me go ahead and find the original problem. So that is how you're going to find the oblique slant asymptotes of each rational function. So you know how to find it, use long division, and you know how to determine if a rational function has an oblique asymptote. All right, so that's the end of this lesson.